Welcome to our Rapid Fire Revision series. Today, we're diving into the magnetic effects of electric current for Class 10. Get ready for some serious electrifying knowledge. We're talking invisible forces, coils that act like magnets, and even how electricity is made. So strap yourselves in, get your thinking caps on, and let's get this rapid revision rolling. Okay, imagine a magnet. It's a simple object, but it holds a fascinating secret. You can't see it, but it's got this invisible force field around it, right? That's its magnetic field. This field is what gives the magnet its power. It can push or pull on other magnets or even some metals. This interaction is what makes magnets so useful in everyday life. We measure magnetic fields in a unit called Tesla. Named after the famous inventor Nikola Tesla, this unit helps scientists quantify the strength of a magnetic field. What's important is that we can actually see this invisible field using iron filings. These tiny pieces of iron reveal the hidden patterns of the magnetic field. Sprinkle them around a magnet, and they'll line up along the magnetic field lines, kind of like tiny little compasses. This simple experiment makes the invisible visible. Speaking of compasses, they work because Earth itself is a giant magnet. The planet's core generates a magnetic field that guides compasses. It's got a magnetic field that surrounds the whole planet. This field protects us from harmful solar radiation and helps animals navigate. Now, here's where it gets even more interesting. The relationship between electricity and magnetism. Electricity can create magnetic fields too. This discovery was a game changer in the world of physics. When electricity flows through a wire, it creates these invisible circles of magnetic force around it. This principle is the foundation of electromagnetism, which powers countless devices in our modern world. Alright, so we know that electricity flowing through a wire creates a magnetic field, but how do we figure out which way the magnetic field goes around the wire? That's where the right-hand thumb rule comes in handy. Imagine you're holding that wire in your right hand with your thumb pointing in the direction of the current. Now, curl your fingers around the wire. That, my friends, is the direction of the magnetic field. This rule is super useful for understanding how all sorts of electrical devices work, from speakers to motors. And remember those concentric circles we talked about? They get weaker the further away you get from the wire. We can actually make the magnetic field stronger by looping the wire into a coil. Remember how we said looping a wire into a coil makes the magnetic field stronger? Well, if we really want to crank up the magnetic power, we can create an electromagnet. To make an electromagnet, we take a coil of wire and wrap it around a core made of a special material called a ferromagnet. When we pass an electric current through the coil, the iron core becomes magnetized. And the best part is, as soon as we switch off the current, the magnetism disappears. Electromagnets are everywhere. They're in your headphones, your doorbell, even those giant cranes that pick up scrap metal. The more turns of wire we wrap around the core, or the more current we pump through it, the stronger our electromagnet becomes. Okay, get this. If we take a wire carrying an electric current and put it near a magnet, something amazing happens. This isn't just some random occurrence, it's a fundamental principle of electromagnetism. The wire experiences a force. This force is called the Lorentz force, and it's what makes electric motors spin and speakers blast out your favorite tunes. Without this force, many of the devices we rely on every day simply wouldn't work. But how do we figure out which way this force will push or pull? Don't worry, we've got another handy rule for that. Fleming's left-hand rule. This rule is a simple yet powerful tool that helps us predict the direction of the force. Here's how it works. Point your thumb, index finger, and middle finger of your left hand so they're all at right angles to each other. It might feel a bit awkward at first, but trust me, it's worth it. Your thumb represents the direction of the force, your index finger represents the magnetic field, and your middle finger represents the current. It's like a secret code that unlocks the mysteries of electromagnetism. So if you know the direction of any two of these, you can use Fleming's left-hand rule to figure out the direction of the third. This rule is incredibly useful in both theoretical physics and practical applications, making it a must-know for anyone interested in the field. Alright, let's talk about electric motors. These fascinating devices are the unsung heroes of modern technology. These ingenious devices take electrical energy and turn it into mechanical energy, making them essential for all sorts of things that move, from your blender to electric cars. Imagine your daily life without them. No smoothies, no electric vehicles, and no washing machines. At the heart of every electric motor is a coil of wire called the armature. This component is crucial because it interacts directly with the magnetic field to produce motion. This armature is mounted on an axle and sits within a magnetic field created by either permanent magnets or electromagnets. The magnetic field is what makes the magic happen. When we pass a current through the armature, it experiences a force thanks to our old friend, the Lorentz force. This force is what initiates the rotation. This force makes the armature rotate, and because it's mounted on an axle, the axle rotates too, giving us mechanical energy. This rotational motion is then used to perform various tasks. To keep the motor spinning smoothly, we use a device called a commutator. The commutator ensures that the current direction in the armature coil is always optimal for continuous rotation. Electric motors are everywhere, and they come in all shapes and sizes. From tiny motors in your smartphone to large ones in industrial machines, they are indispensable in our daily lives. Now, let's flip the script and talk about how we can use magnetism to create electricity. This mind-blowing phenomenon is called electromagnetic induction, and it's the principle behind generators, which power our homes and cities. Imagine a coil of wire and a magnet. If we move the magnet towards the coil, an electric current is induced in the coil. This happens because the moving magnetic field creates an electric field, which in turn pushes electrons around the coil, generating an electric current. The faster we move the magnet, the stronger the current. This relationship between magnetism and electricity is described by Faraday's law of induction. Electromagnetic induction is everywhere. It's how generators work, how transformers change the voltage of electricity, and even how wireless chargers power up your phone. Okay, time for a quick but important distinction, AC and DC. No, we're not talking about the rock band. We're talking about two different types of electric current, alternating current, AC, and direct current, DC. Direct current is the straightforward one. It flows in one direction only, like the current from a battery. Think of it like a one-way street for electrons. Alternating current, on the other hand, is a bit more adventurous. It changes direction periodically, flowing back and forth like the tide. The electricity that comes out of your wall outlets is AC. DC is great for things like batteries and electronics, while AC is more efficient for transmitting electricity over long distances. That's it for our rapid-fire revision on the magnetic effects of electric current. You've learned about invisible forces, magnets made of wire, and even how electricity is generated. Give yourselves a round of applause. Remember, this is just a quick overview. There's a whole universe of fascinating details to explore within this topic. Don't forget to like, share, and subscribe for more revision videos. See you next time.